Hi YouTube, I'm Utilyre, and for the past month I've been working on this multiplayer online game from scratch, Asteroids, because I use the game engine. Though I did all the networking myself, so it's fair to call it from scratch. So on the screen you see two windows beside each other. One of them is the left one actually, represents the first spaceship, you can say, and the client on the right represents the second spaceship. And you see this floating window, and this is just the server running the game, which you can see it's running at 10 fps. That's the reason for the lag, so do not worry about that. Though despite the 10 fps running on the server, both clients run very smoothly at 120 fps. So let's get down to explaining how it happened. So, do I use the slide? No, I won't. So as I said, I use UDP to implement this. UDP is this kind of a protocol thing which is not used quite often on the web, though it's used frequently for game engines and like all the stuff. I don't know every single one of them, but there are properties to UDP. One of them is that UDP is unreliable. So if you send a packet, you don't really know if the other side has actually received it or not. UDP might not error, but the other side may never receive it, and it doesn't have any order guarantee. So if you send 1 2 3 5, the other side, the other peer, may receive 4 2 3 1 5. There is it may not even receive one of them or two of them. So there is no guarantee at all, and it is connectionless, which kind of makes it a pain in the ass to work with. So like with TCP, you basically accept connections, and TCP just establishes this connection for you, makes sure everyone is on the same page before it begins transmitting and receiving the data. But with UDP, you only really listen on a single port, and when the client send you something, you just receive that this guy with that address has sent this. So it's hard to manage your control flow, if that makes sense. And it is datagram oriented, and that means, unlike TCP, where you just have a literal stream coming at you, you can just read 10 bytes, then read 2 bytes, then like do however many reads you want. But with UDP, when you read something from a connection, like if you read 20 bytes and the actual datagram was 40 bytes, you never receive those 40 bytes ever again. So it comes in datagrams, not streams of bytes. And this brings up the question, why not just use TCP? TCP is great and all, but once you get into game dev, it's not that useful. So you can see some cons I put here on the screen. They are not actually cons in the place that TCP is used, but when you want to use a protocol for something like you want to send a lot of data, but a lot of it will be outdated no matter what. So you don't really want to make sure every single piece of data is delivered, and TCP does that, and this results in your game just falling behind the actual state once you have like 5% packet loss. Let me actually show you this if I can find it. Yeah, you can see by the way, really great article series on Gaffer on Games from Gaffer. And you can see this is the client and this is the server, if that makes sense. And he introduced 250 milliseconds of latency and 5% packet loss, and the server is just already choking, like it's just updating at such a slow rate. And this is just because TCP wants to make sure you receive everything. You can see the state is the same, but it's delayed and lagged. So we used UDP, and my reason for using UDP was neither the latency, the packet loss, whatever. I just wanted to learn how UDP works not under the hood, but how you can use UDP. So I did my own custom protocol on top of UDP to make it at least usable for my application. I call the protocol MCP. It doesn't stand for like a cool acronym or whatever. It's just my custom protocol. That's what it means. So what it introduces is sessions. So didn't I just throw away TCP for sessions? No, I didn't. I really need sessions to be able to do anything. Like, not even everyone needs a session to be able to do anything in a multiplayer game, because you actually want to know who has sent it and do the stuff that you want to do with it. So I implemented sessions and it kind of works, but a session without a handshake is only ever gonna work locally. Like it works even on wireless networks, but once you do it like outside of your local network, you can't really guarantee if you have actually established a session or that you just think that a session is established. So you need handshakes, and it's work in progress on the GitHub. I'm gonna link you the GitHub in the description if you want to help me with that. But this MCP package also has broadcasting support, so here you can how many asteroids do we have right now? Anyway, you can see the state is obviously being broadcasted to both of these clients. So that was also what I needed for this game to work out. So I did this foundation thing and then moved on to really figuring out what it takes to make a multiplayer online game. So as I mentioned earlier about this article, this is a fantastic article series. I really recommend reading it. I will link this in the description, but like it goes through not everything, but things you need to know before you get started doing actually multiplayer online games, or even MMOs, who knows. So I read all this and figured that there are 3 approaches to making this kind of games. One of them is deterministic lockstep. This one is kind of simple because I think it is really stateless, if that makes sense. It's just like reproducible states. Yeah, it's reproducible state. So with this approach, you send inputs, and each side of this network figures out the state purely based on the inputs. So this sounds really great, but for a game that is like this, you can imagine all these positions, velocities, accelerations, even rotations are floating point numbers, and we all know that 0.1 plus 0.2 does not result in 0.3 in computers, and that's because floating point numbers aren't really accurate in calculations. So or a better term to use is that they are not deterministic. So we can't really rely on this approach or take this approach. So we go to the next one, snapshot interpolation. This is actually, spoiler alert, I actually use this approach for this game. So if it was you that presses these buttons, you would have noticed a little bit of delay before you see the reaction on your client. So that's because we are using snapshot interpolation basically. With this way of doing things, you treat your clients as IO devices basically. So if the player presses a button or just does any kind of input, that is the input is then sent over to the server. The server does all the state updates, calculations, whatever, and then sends back the resulting state to the client. So the client is just responsible for capturing inputs, sending them to the server, and then receiving those snapshot updates and applying them to the render basically, so just showing it on the screen. And this other one, which I did not use mainly because it becomes too complicated. The third one is just, it's a snapshot interpolation, but like the way I think about it is that it's snapshot interpolations done in a distributed way. So you send those inputs and get the snapshot update, though to save bandwidth you do not get every state all at once. You only get things that are in priority, and like you do your state updates with those, and then based like for those you didn't receive any snapshot updates, you then extrapolate, yeah, that's a word, and like update them on your own, because like say if a ball just moves there, like in a non-football game, a ball is moving on the ground, so you don't really care that the ball is like hitting the wall at what moment. You just want a ball moving on the ground. So you can do that yourself and not rely on the server. That's the whole point of state synchronization, and that removes like many problems from this previous approach. But I decided to go with this because it made the most sense to me, and it was a bit simpler, and I didn't need to debug so many things all at once. So we did snapshot interpolation. As I said, there are two parts. There are mainly two parts: input and state update. So let's discuss the input part. While doing this, you really want to have order and reliability in your underlying protocol. But since we're using UDP, you don't get that. So you need to implement that yourself. And there is a nice trick. I don't think it's introduced by Gaffer, but it's certainly mentioned here in the deterministic lockstep article. And let me show you the parts if I can figure it out. Yeah, it's the can we do better than TCP part. So this trick is quite simple, and it's just changing the rules of the game. So you attach a sequence number to each of your inputs. So maybe I should actually show you some code when I'm thinking about it. If I go to the input struct, here is a sample input struct, and actually this is the one used in my game. You have a couple of booleans which represent whether a button is pressed or not. So you got left, down, up, right, and space. So on each frame you construct this input struct, instantiate it, set the correct values, and then you pack it into binary and send it over the wire, right? Send it to the server. And while you're doing that, you also attach a sequence number which increases every frame for each input. So your first input has a sequence number of 1, your second has a sequence number of 2, and so on. So doing that, you also group your inputs together. Like, you always send all inputs from the beginning of the game. So your first frame you send 1 input, second you send 2 inputs, third you send 3 inputs, and you get the idea. This way the server, the protocol doesn't really need any order reliability, because you're just sending them in arrays. Basically, they're just redundantly including all the inputs that you have ever had, and the server can just have them all. Like, even if one of them delivers, then the server has all of the inputs, right? And just to avoid having to send like increasingly bigger packets over time, you just the server just takes it received inputs 1 through 7, right? It takes 7, the latest inputs index, then it sends an acknowledgement datagram back to the client, so the client knows that, okay, the server has gotten this far, has gotten to the input number 7, so I'm just not gonna include any inputs before that, including the input number 7. That way, when I tried it, I was just sending I think 1 or 2 inputs per frame, so it wasn't a big of a deal. And you can already see that this struct is not that big. We got 5 booleans which we can just pack into a single byte. It's not even gonna take the entire byte. So like each frame maximum a few bytes are gonna be sent to the server, and we got both reliability and order. So just going back to the UDP properties, we got this through the way we sent stuff, and we got connections through the MCP implementation, and we kind of just used datagrams to our advantage to just simplify every implementation. If you don't know, just dealing with streams, though it sounds simple, you just pass like streams of bytes everywhere, do the IO writer or IO reader thing, but it becomes a nightmare just doing that from scratch. So data oriented is kind of makes UDP kind of simpler. Hot take probably. So let's go to so we know how inputs work. So now the server receives inputs, each frame, each simulation iteration, each simulation step, whatever you want to call it, and updates the states accordingly. And now the server needs to send back state updates. So how do we do that? we do the same trick as we did with inputs. We attach a sequence number to each state update, and by the way, the sequence number is not the same as the input sequence number. They are just different when incrementing them. So we attach that sequence number and then broadcast to all clients, and MCP already has a broadcasting feature, so that's gonna be easy. So yeah, we broadcast, and then when the client receives these states, that sequence number we just attached to our state becomes useful. How? So the client keeps track of its latest index number that has received, and if we receive anything that's older than that, we're just gonna discard that state because we don't need it anymore. And that's for the index. So there's one last trick we do to get the smoothness. You see, where is my first spaceship? To do this smoothness on the clients, the server is running at 10 FPS. Why am I pointing with my fingers? The server is running at 10 FPS. You can see it looks kind of laggy, but the clients run smoothly despite that. How cool is that? Oh, wrong workspace. So the way we do that is that we linearly interpolate between the latest two states, and that's gonna be it. We got smoothness. And it's not easy to figure that out, but once you figure it out, it's just kind of simple to do. So we need to keep track of two states, which is gonna be hard on memory, but here we are. So now we got an idea of how all this works on paper, but going into the implementation, you realize things that you wouldn't know beforehand, obviously. And there were two things that made me rewrite the entire project twice. So the first attempt, I realized that I would need so there's some there's queues that I use for just processing all this stuff and making sure everything is non-blocking and all that. But this goddamn queue has to be separate for each client, and it's not obvious to know this at the beginning. So I did a single queue for all the clients, and what I ended up with was that like one client would take the lead and all the messages in that queue was from that singular client, while all the other clients just did not have anything to say. Like they did have something to say, but they didn't get a chance to manipulate the state because that one client just got in their way all the time. I may be able to show you that, or maybe I won't find it, I don't know. Yeah, let's just give it up because it's gonna be too hard to find. So that's that. And the other thing is that I didn't really go through a full rewrite for this, but I partially rewrited the game logic and state and all that because of this. And this is that, like, you want to make sure your simulation loop and each of your clients' game loop run at like a constant frame rate no matter what, and you really don't want slow connections to interfere with any of these loops. So you're gonna need to, we'll see in the architecture diagram, by the way, just to give you a slight show, here it is. But before we go there, you need to realize that you need these two loops to be independent of the network. So how do you do that? Is through setting up a queue so that messages you receive are put into that queue, and then these game loops and simulation loops will take something out of that queue once they need it, not like block on the queue or on receiving a message just because they wanna update the game. They don't need that, right? Okay, so here's the architecture. Let me zoom in. So yeah, just to like just to give you a look, the blue ones are the client side stuff, and the green ones are server side, and yeah, that's basically it, except that uh, these dashed arrows are there to like represent weak message passing. Oh, I don't know what that term is, but like I want to indicate non-blocking. So there are, I think, three data flows, if I remember correctly. Yeah, there are three. One is that you got a server running, just the simulation is running, the accept loop is there, and by the way, every single one of these shapes represent a loop on either the server or on the client based on their color. Again, so what I was saying, you got a server running, no clients are there so far, but one client comes up and wants to join the game. So it sends a dial, or like in lower level terms in my implementation is a flag join datagram. Basically it is there to signal the server, hey, I'm here, I want to join the game. How do I like it? How do I do that? Not that it actually asks it, but like to give you a cool story, it dials the server receives that in the accept loop, then it's gonna create a separate receive loop just for that client, and then once like it creates that, and also notifies the simulation through this loop that, hey, a new client has joined. So you may it tells the simulation you may need to like create a player in the game state or do something, I don't know, I'm just gonna tell you somebody joined. So that's the first workflow. The second workflow comes in when like your client has started and wants to send in inputs. So the game right here just like constructs those input structs we talked about earlier, constructs these, groups them together like the way we said. It's gonna redundantly include all the unacknowledged inputs and then send them to the server, and then the server is gonna receive it in its receive loop. Once it has received it, it's gonna put it in the queue so that the simulation is gonna be aware once it wants that input, not like forcefully tell it to stop and wait for this input. It's just gonna be there for the simulation to pick up later. So it's gonna put it in the queue, the receive loop is gonna put that in the queue, and then acknowledge the game that, okay, I have received up to this input, do not send me again these anytime later. So it sends an acknowledgement packet, the game receives it on its own receive loop, and then in a non-blocking fashion it does some mutation to the local state so that everything's cool. And one last workflow we got remaining is the the last workflow is after the simulation has picked up all the inputs from all the clients, and then it processes it, updates its internal state so that it has like all the game logics checked, all the collisions checked, all the movements done, everything is cool now, except that it wants to send back the state updates to all the clients. So it's gonna broadcast a state update with that index we talked about earlier, and the game is gonna receive it in its receive loop, and then again in a non-blocking fashion do a mutation to its local state, so like everything is fine. And that's it, that's gonna be it. One thing I wanted to point out is that I actually forgot what I wanted to point out. What did I want to say? I don't have it in my notes. So maybe I should have forgotten that anyway. Interesting. There is a like, if you want to do this kind of stuff, please have a loop, separate loop for receiving from the network, but you don't need to have a loop for sending them. Like you could, but you will introduce some delay, which is not cool. You can just say try to send this. If you couldn't send it, I don't care, just try to, and like it's just a fire and forget kind of thing. So you don't block your main loop, and also you, like, I don't know, you didn't introduce any delays. So thank you for watching. If you like these kind of long talks of me, like going through stuff and sharing all the stuff I have figured out, please leave a like on the video, subscribe if you like to watch more, follow me on Twitter if you'd like to. My handle is Utilyre on all platforms, so Twitch, YouTube, even GitHub. Let me even show you my GitHub. And by the way, if you follow my Twitter account, I post updates about my game rather frequently, like more frequently than these videos, so you may want to check that out. And like, this is the repository, all the links are gonna be in the description, by the way, but here's the repository if you want to check out the Asteroids game. Is on the demo Asteroids branch right now, but it will soon be merged. If you are like, if you use it, if you find an issue, please file an issue, or if you'd like to contribute to my work, then open a PR, I guess. So thank you for watching, and I'll see you guys later.